move on to the next topic, and the next topic is laws of motion. Right. So, in laws of motion, we are going to look at what are the various law that relates the different types of forces that are commonly encountered in mechanics. Right. So the laws relating the forces are the fundamental concepts to be discussed over here. So first, let's look at the types of forces to start with. Right. So the types of forces. First type of force is called as a field. Right. So the field force, right, are those forces which contact between two objects wherein the contact is not required, right? So forces without contact, right, of any two objects. For example, the gravitational force, electrostatic, electromagnetic, the weight, etc. Right. The first one is gravitational force. Then the second example could be electrostatic force, electromagnetic, weight, etc. They fall under this category. That's the first example. Then the second type of force is called as the contact force. This is a kind of force when two bodies come into contact with each other. Normally, this kind of force is equal and opposite in magnitude. That is obvious because two forces when come in contact, right? We have to apply the other laws as well. Because of the laws, we will see that that's there will be equal and opposite forces. So we can write this is the forces between two bodies in contact, right? Because of this, we have the equal and opposite nature of force. All right. So the most common type of the contact force is called as a friction. All right. Let's try to define the friction now. Let's just give an example. Say this is some surface on which we have placed, say, a body. Okay, this is a body, and on this body, I'm placing another body. Okay, so this is body A, body B. All right. We can say that there will be a frictional force that is exerted between the two objects, right? Whenever there is a rough contact between the bodies and the bodies move in with respect to each other, there is a relative motion, right, between them, right, without losing the contact. For example, let us say the body A moves in this direction because of certain force that is being exerted on that. Let's call this as F1. All right. At the same time, this is going to move to the left because some other force is being exerted. Let me call that as a force F2. Right? So the motion is in opposite direction. Let's say the contact between A and B, that is denoted by this region, right, is not very smooth, right? It's not smooth, it is hard. It's a rough surface. So because of that, there will be a contact force that is exerted between the two bodies. All right, there will be a contact force which is called as a frictional force. So at this particular point, I can mark that there is a F. Let's look at the details of this F later, but there is what is called as a frictional force. And also you have another force that is occurring at the point of contact. It is called as a normal force or normal reaction, to be specific. Exactly, that happens at the point of contact itself. So it is always perpendicular to the direction of motion. So I'll denote this as this. These are the two common contact forces. All right, so that I get. So if I assume that this what you call surface is very smooth, then there is no friction that is that's going to come into picture at the contact of the body B and the ground or the surface. But always you have the normal reaction, right, coming into picture. So generally two contact forces are, one is F, which is called as the force of friction. Right. Then the other one is N. So N is nothing but the normal reaction. So this kind of forces do exist whenever we are looking at the contact forces. And the next category of forces belong to a class where we call as the forces that are going to arise because of attachment to another body. So we make a new category that is called as attachment to attachment to another body. Whenever a body is attached between whenever a body is attached to other body, right, we have a new type of force that is coming into picture. So the common force is called as a tension. Under such condition, this is called as a tension force. The T, right, is actually uh, if you want to attach a body to other body, you have to use something like a string, right? When I have a string, you have tension in the string, right? Again, if you instead of a string, if you use a spring, that is also going to be the similar case. Or if you try to uh, connect two bodies through a pulley, right? Again, you are going to see there is a concept called as uh, the tension. All right, let's discuss about that. So tension, right, is a force in string, or it can be spring, right? String or spring connecting the two objects or two different bodies. If two bodies are connecting through string or a spring, you have the concept of what is called as the tension coming into picture. Let's look at some examples. A very simple example is connecting two different bodies. This is a body of mass m. Okay, and let us say I have another body of a different mass. So say this is m1, this is m2, and let us say we are connecting the two bodies by means of some sort of a string, and we are trying to pull one of the what you call as masses, right? Say there is a force F. Okay, so you see that this the mass m2 is going to pull the m1 to this side, so it brings up a tension over there. At the same time, m1 will pull the m2, right, with the same amount of force, the same force. Okay, so that is the tension over here. Overall, that force represents the tension. Right. Normally, under this case, we assume that the spring, sorry, it's a string, not a spring. The string that we connect is not going to expand. Inextensible string, we call. Okay, it's not an extensible string, so there is no force that gets absorbed, right? And as soon as we apply the force, the tension T builds up. This is what is the basic concept. Anyway, so what happens if you use a string instead of a string? If you use a spring, right, some amount of force is getting absorbed over there. So we'll look at that concept later, but still you build up the tension inside that. Also, you can give another good example like this. Let us say we have this is a surface. Onto this surface, let us say we connect say a pulley. So this is a pulley that we are going to connect. This is the center of the pulley. So the center, we can connect it to the surface by means of some sort of connection. Okay, it is connected. Now to this, on both the sides, we let us say we are trying to hang various mass. Okay, one mass, this, another mass could be this one. Okay, so this is mass m1, this is m2, and this is how they are connected. All right, so again we can see that, right, this is going to pull the thing downwards, this is also going to pull it downwards, right? There may be a resultant motion, right? If m1 m2 is larger, definitely m1 will move upwards, m2 will move down, but the tension in the string can be represented just like this. The one each of the mass will try to pull it towards itself. Okay, so that's all. Again, there will be an acceleration, etc. will come into picture. That's fine. You can consider that at a later stage. As of now, our intention is just to learn the type of force. All right. If at all it is a spring, right? We have another equation. Force is equal to k into x. Okay, x is the distance traveled. Anyway, that will come later. Anyway, right now I don't want to. The next type of force is called as the hinge force. Okay, now the hinge force is going to exist in a specific location called as a hinge. Let's try to define the hinge now. Okay, this kind of representation. This is a wall, right? On a wall you have, right, a structure which supports a rod like this, and this is, let us say, we are connecting a string to this, right? And we can keep the objects here. This is something like a shelf or something. Okay, let's this kind of, this is the wall. This is a ball. So this is a so we have a rod over here, and this could be a string, and this is called as a hinge. So when we have a hinge in place and we put an object on this rod, right, we can see that variety of forces that might arise, right, at the position of the hinge, right. Hinge may feel, right, at this hinge location, you can find a force like vertical force and a horizontal force, right. Otherwise you can also get a resultant of this, because I may have a vertical and horizontal, which can be considered as the resolved forces along x and y axis, and we know that we can get a resultant, right. We can convert that into resultant. So resultant and direction, or the vertical and the horizontal components of forces, do exist at a hinge. So because of which we call hinge forces are normally two forces. One is a horizontal and a vertical. Two components will come in, right, at a hinge. Or otherwise we can assume that you can find the magnitude and direction. But anyway, I don't want to write the magnitude and direction now, because of, anyway, we can convert it, right? So you can have hinge force can be found by using maybe a horizontal component, right, that is denoted H, and you can also find out what is called as a vertical component V. Okay, you can have a horizontal and the vertical components present to it. Okay, now in order to represent the nature of a forces, where it is acting, and is it away from the body or towards the body, right, etc. In order to represent that in a very complicated force system, right, if you try to represent even the bodies over there, it becomes very complicated, right. So there is one technique which is used to represent the forces in a system, and that is called as a free body diagram. Okay, so this means it's a diagrammatic representation isolated from its surroundings, showing all the forces acting on it, right. So you try to represent either a single body or the group of bodies or a subsystem of bodies. You have to show them in such a way that they have to be isolated from the surroundings. Surroundings you should not show. right? Even if you don't show the body as it is, that's fine. You can even consider the center of the body as a center of mass, and all the forces can be assumed to be acting upon that particular point, right? So isolated from the surroundings, with all the forces acting on that body or the subsystem of the bodies have to be shown over there. If you try to represent that, then that becomes a free body diagram. Let's quickly go through some of the free body diagrams in general. Okay, so then we will be using them in many problems to simplify the situation. Okay, the first one is, this is the actual diagram, and later on the right hand side we write the free body. Okay, so this is the system, right? This is assumed to have certain mass m. M is the mass of the body. Now, what is the force acting upon? Now you can see that this is actually simply, you can consider that there is a stone which is lying on the floor, right? Mass is m, and I don't see any force that is actually acting upon, right? But if you look carefully, yes, there is, or there are forces acting upon. You have option, like you can simply consider the body as it is, like this, and you can show what is happening with it. So you assume that there is a center. This is the center of the mass. On this particular point, you can see that the weight is acting downwards, right? So you can definitely write one force like this, which is nothing but, right, this is the weight, W equal to mass into the gravitational of the acceleration due to gravity. At the same time, we know that since this is lying on a surface and the body is not moving to the right or to the left. It's not moving. So there is no friction. Okay, but even though there is no friction, there is a normal force that is acting upon, because it is a contact. There is a contact that is happening. Whenever you have a contact, you have contact force coming into picture. So I have to denote that. So let's do it in this way. So this is the upward force. This is denoted by capital N. Right. So this is the free body diagram of this case. All right. Let's move to the next example. Example number 2 is, okay, there is an object like this. Okay, let us assume that this particular body is getting contacted at two different surfaces, right? Say the surfaces are like this. One is over here, and there is another surface where the contact happens somewhere here. Okay, so this is the reference plane where it's going to touch. All right, so this is the system. Let's assume that there is what is called as uh, a mass that is denoted as mass of this body, say m. M is the mass. All right, now I want to write the free body diagram. All right, so here again, I want to show you that the free body diagram, you don't have to write the body as it is. Simply, you can represent the center of the body or the center of mass. So center of mass is a point, right, on the body where you can assume that the whole mass of the body is concentrated. All right, since, right, this object is kept, right, contacting two different surfaces, the weight of the body is always downwards. So this is the obvious case where the body's weight act perpendicularly, right, downwards. So we indicate that like this. Okay, so this is that force which we were talking about, acting downwards, right? So this is the weight of this object. W is equal to the mass into the acceleration due to gravity. Okay, that's the first one. Then you can see wherever the objects, two bodies touch each other, we know that there has to be a contact force. That's perfect. And we know that the contact force is always perpendicular to the surface. In the sense, I have one contact here and one more contact here. So from both these locations, I have to have two different forces, right? It is perpendicular in the sense, definitely it means it will pass through the center of the uh, circle that we are writing. So both forces will act like this, right? You have options. I will show you both the options now. One is that you can uh, draw something maybe like this. So this is, you assume that this is one of the force, right? This is the normal force at this point, right? I am writing it over here. Okay, that's one force. Similarly, you can have another force. So the second force is acting here. This is actually coming from right side to the left. So you can have a force like this. Again, that is passing through the center of the sphere. All right, this is N2. N1 is the indicating normal from one side, N2 is the normal from other side. But I'll show you more clear picture, right? You can actually write it in a different way. So this is a vector, right? So vector can be actually moved to the other side as well. So I can equivalently write this as, the first part will keep it as it is. So there is a, this is the center of mass, and there is a force that is acting vertically downwards like this. Okay, this is W is equal to M into G. Now, instead of writing a force on this side, I can actually move this to the other side of the center, right? The central point where we consider the whole mass is concentrated. I can move it to the other side, but don't change the angle and the direction. Don't change the angle. Keep it same, but move it to the other side, like this. So this could be the N2, and we can have the N1, instead of writing here, right? I will move to the other side. So that is, instead of writing here, I will write it on the other side. Say like this. So make sure that it passes through the center. Okay, let me correct this. So I just want this to move to the other side properly through the center. So this is the center, and I will write like this. So you see, this is N1. Both are correct, right? You can use this or this. As you can move the forces from along the straight same line, if you move the force further, there is no difference because it's a vector. So magnitude and direction is important. Whether I write here or I write here doesn't matter. As far as this length is same, and the angle is also going to remain same. So that's what we had studied in the topic called the vectors, right? So we are sticking to that. So this is the second option, or the second technique of performing what is called as a free body diagram. All right, so each body can be considered separately to draw this. Let's go for one more example of free body diagram. Let's say this is a surface. On this surface, let me say that we have three bodies stacked one on the other. That's the body number one, and the second body, and I have the third body on this. All right, so let me say this is okay. Let's denote A, this is B and C, and C is actually resting on a frictionless flow, let's say, okay, on a smooth flow. Right, now you can write the free body diagrams. I cannot write the free body diagram for the whole system. I have to write it one by one. So for the first one, right, that is for A, right, I'll write FBD, free body diagram of A. First I'll write that. So how it's going to look like, consider the center of mass. Over there, there is a, because of the mass of that object A, there is weight, that is W of A, right? Since the mass is not given, they have just given A, indicating that that is the object A. There will be a weight of that object, so I denote this is WA. And at the same point, you have a normal that is, right, arising because of the contact between A and B, right? Because of that contact between A and B, you have a normal force that is acting upwards. All right, so that's the free body diagram of A. Next, let's write the FBD of B. Looks very simple, but we need to be careful. All right, now, so I have to consider how many contacts B has. By default, right, definitely the center of, this is the center of B. There is a weight acting downwards, that is WB. Okay, but you see there are two contacts. So because of the two different contacts, right, you have two forces acting, one downwards, that is the N1 which you had written earlier in case of A. The same force, actually the N1 is exerted by the body B on A. So when that happens, A will reply to that with the same amount of force in the opposite direction that acts on the B, and we have marked that downwards now for B, because B pushes A upwards means A is going to push B down, so that's why, that's the reason. And there is another contact, that is C. There is a contact between B and C, which means, right, the C will push B upwards. Okay, so that's what I'm trying to write it over here. So this force is, there is a force that is upwards, right? And this force, right, is nothing but N2. I'll call N2 because N2 is a normal force between B and C, right? Then we'll write the free body diagram of, say, C, right? Very similar logic. This is the center of mass for C. The weight of C will act downwards. Okay, so this is WC. Right. Now, from the top, B is going to push C downwards. So there will be a force N2 acting on this. And since the surface is frictionless, that means C is not moving. There is no friction. But definitely because of the contact, you have a normal force coming into picture, that is N3. Right? So you see, like this, we can write the free body diagram. Definitely, you can even represent the C like this. Doesn't matter. It's going to be fine. B and C, the bodies can also be shown. But the basic idea or the basic concept that I need to remember when I try to draw the free body diagram is that, right, I have to separate the object from the surroundings. When I write B, I should not show A and C like that. Okay, let's go for another quick example related to the related to the free body diagram. Okay, this is the next example. Okay, now we have to write this one. Okay, what is the equivalent the free body diagram of this particular force system? All right, let's try to write that now. So say this is the center of the mass, right? So because of the mass is present, so the mass will always generate a force downwards, which is the weight. Okay, so this is W. I can write the W is equal to the mass into the gravity. Then, so there are two strings connected, one here and one here to the body. So the strings, since they are connected, they're actually, this belongs to which case? This belongs to a case where the force is generated, right, because of attachment of, right, two bodies. So since we are attaching the bodies here, right, that kind of force do exist. So the forces are denoted by the word string. Okay, so there is a string connected exact that direction I have to mark, because it is going to be presented at the same angle and the same magnitude. So at a theta, I call there is a string. This is a string, so there is a tension. Okay, the reference point tries to pull this mass towards, right, that particular object. All right, at the same time, horizontally towards the left, this is connected to a body, a reference point. So along that also I have another tension, so I'll call this is T2. Right, you can see that, right, these are the forces of the system. So two tensions and one weight, that is downwards. All right, now let's move further. The next concept is called as the equilibrium. So we need all these terms to understand the concept of laws of motion. So we are trying to explore those topics first. Okay, right. When multiple forces act on a body and the resultant is zero, okay, with no turning effect, right? Such forces are called as, right, they are the situation of the object is said to be in equilibrium. How much ever forces are acting, may be acting on the body is not going to move, or body is not going to turn. There is no turning effect and there is no resultant force, right? Such forces and the object are said to be in equilibrium. All right. So if multiple forces act upon a body with no resultant and no turning effect, on the body, then the then such a system actually, then the system is said to be in equilibrium. Right. So whenever there is a system acting upon by multiple forces, such a way that no, the resultant is zero. So what is the condition for equilibrium? For equilibrium, the net force acting upon a body should be zero. And there is another concept that is actually, right, the rotational force that might. So whenever multiple forces act on a body, there may be a rotation also, right, as a result of this. That also should not be there. So rotational force is called as a torque, and we'll say that even the torque is zero, right? Two things are there. For specific type of forces which act on the same point of the body, we call as a concurrent forces. For concurrent forces, no result. For non-concurrent forces, there is no turning effect. Anyway, we'll see that later, but let's, before looking into the concept of equilibrium, let's try to look at the concept of resolution of a force once again. Already we have discussed this, but let's go for a quick review of that. Okay. Resolution of the forces. Right. Now, let's go back to our x and y axis. So this is x, this is y. If we consider a force like this force can actually, let's say this is the force F making an angle theta with the x-axis. We can split this into two parts. One is the force, the component of the force along x-axis. One more is the component of the force along y-axis, Fx and Fy. So if the angle is given with respect to the x-axis, right, then Fx becomes F cos theta and Fy becomes F sine theta. This is the first concept. And the second one is like this. The second concept is simply we consider another diagram of a very similar case, okay, wherein this is the x-axis and this becomes the y-axis. The force is going to be very much same. This is the force F. Now you see the angle is not measured with respect to x but y. So still I can split this into two components, one along x-axis and one along y-axis. So along y, whatever you have is Fy and Fx. But the equations change now. For this situation, the Fx becomes F sine theta and Fy becomes F cos theta. Okay, now, right, let's go for a quick problem. We need to bring the concept of what you call the we have to consider which is positive, which is negative, right? That also comes into picture. Already we have studied that already, so let's solve some of the problems very quickly. This is the first force. This is 35.75 Newton at an angle 22 degrees. And we have another force that is acting upon over here. Okay, so this is 83.67 Newton, making an angle of 31 degrees. So find the x and y component of the forces. Okay, so the first force F1, I'll call this is all right, let's call this is 35.75 Newton, and the theta I'll call it as theta 1, that is 22 degrees. So you can see that the first force, this force is actually our first scenario we considered, right? So you can see that the first scenario is nothing but this one, right? Force is present and sorry, not this one, the one before this one, this scenario. Okay, we have the force and the angle is given with respect to the x-axis. So that's the first case. If the angle with respect to x-axis is given, then we can write the force 1 along x-axis is nothing but this is F cos theta. So that is 35.75 into cos 22 degrees. That's the first component. Then F1 along y-axis could be 35.75 sine of 22 degrees.